Hey everybody, welcome back to part 2 of chapter 11 on multiple regression, and today we're going to talk more in depth about multiple regression examples and the output associated with a multiple regression analysis. So let's dive in. So let's say that I've got the following data. We've got 3 different variables. Time with friends, we'll say that's measured in hours per week. Satisfaction with social life, that'll be on a scale of 1 to 15, and happiness will be on a scale of 1 to 10. So I've got 3 numeric variables, and I want to see how time with friends and satisfaction with social life influence or are related to happiness. So which variable or variables are going to be my predictor variables in a multiple regression analysis? That's going to be time with friends and satisfaction with social life. We're going to use those 2 variables to predict the outcome, which is happiness. So when you conduct a multiple regression analysis, oftentimes it comes along with a correlation matrix. And this is just the bivariate correlations of all the possible combinations of 2 of the variables. So in total, we have 3 variables, right? We've got happiness, we've got time spent with friends, and we've got satisfaction with social life. And so it'll give you this correlation matrix, which gives you the correlations for, let's say, happiness and time spent with friends, happiness and satisfaction with social life, and then time spent with friends and satisfaction with social life. So let's just walk through this really quick because you see this stuff in research all the time, and it's a good thing to just know how to look at this and how to interpret things. So for instance, if you look at there's different rows and different columns, right? So the first column is all 3 of our variables, happiness, time spent with friends, and satisfaction with social life. You'll see that the row along the top also has happiness, time spent with friends, and satisfaction with social life. And so basically what you do is you would take the row and the corresponding column, and that is going to give you the bivariate correlation. So you'll see that happiness correlated with happiness would be you take the row for happiness and the column for happiness. But there's no answers there. Usually you'll see a Pearson's R of 1. Why is that? Well, because you're correlating the same variable with the same variable. That doesn't make any sense. So obviously all of the numbers are identical and it'll give you a Pearson's R of 1. But we don't pay attention to that stuff because there's no reason to correlate one variable with itself. So instead, in that happiness column, you can go 1 row lower. So now you're talking about time spent with friends and happiness. Well, what's the correlation coefficient for that? 0.65. And is that a significant correlation? Well, you see the p-value right under it is less than 0.001. That's a lot less than 0.05. So yes, that is a significant relationship between happiness and time spent with friends. Now, let's stay in that same column of happiness and go 1 further row down to satisfaction with social life. So now this is the bivariate correlation of satisfaction with social life and happiness. Pearson's R is 0.50, and the p-value again is less than 0.001, so that is less than 0.05, which is a significant relationship there. It's a positive relationship, so was time spent with friends and happiness, and that would be expected. Okay, now we jump over to another column, which is time spent with friends, and the only Pearson's R that's available to us here is satisfaction with social life. Why is that? Well, because we already know what the correlation between time spent with friends and happiness is. That appeared with the second row and the column for happiness, 0.65. So we don't need the same value basically above with time spent with friends column and the happiness row because we already know what it is. So you go time spent with friends column and you go all the way down to the satisfaction with social life row. And now we have a correlation of 0.70. So it's a strong positive correlation. Is it significant? Yes. At p is less than 0.001, which is less than our alpha of 0.05. So that's significant. So if you wanted to, you could also have these basically the same numbers above what we call the diagonal meaning happiness with happiness, time spent with friends, and time spent with friends, satisfaction with social life, correlated with satisfaction in social life. We don't need that diagonal, right? And you could still put in the correlation coefficients above that diagonal, but they'd be identical to these other ones. And so mostly whenever you see a correlation matrix, you only see values in kind of the bottom left corner, making a triangle of the on the bottom left, essentially. Hopefully that makes sense. We can talk about it more in class if you'd like. So when you conduct a multiple regression analysis in R or whatever software that you prefer, you get a lot of output, okay? And so it can kind of be overwhelming and look a little scary at first, but we'll just kind of walk through some of the more important pieces of it and what you should keep an eye on. So the first thing that happens is you get a model summary, okay? And so it'll say model number 1, which is the model is going to be the two predictors predicting the one outcome variable, right? So time spent with friends, satisfaction with your social life, predicting happiness. That's the model, model 1. The R value, the capital R value, you'll remember from last time, that is the multiple correlation coefficient. So that's the combined relationship of time spent with friends and satisfaction with social life on happiness. That's kind of the combined relationship, 0.985. R squared is literally just 0.985 squared. 0.985 times 0.985 gives you R squared. What is R squared? Remember, R squared is basically the proportion of the outcome that's explained by all of the predictor variables. And so what this would, how you would translate this into just sort of like an interpretation would be 97.1% of happiness, of the variation in happiness, 97.1% of the variation in happiness is explained by time spent with friends and satisfaction with social life. The adjusted R square is basically the same thing as R squared, but the statistical software basically also takes into account the number of predictors you have and your sample size. And so it creates kind of a more conservative estimate of R squared. Most people in research use this adjusted R squared as opposed to the regular R squared. It's basically just you get a penalty if you have too many predictors in your model, because a lot of those are going to have kind of overlap in their effects on the outcome. And so it's just a better estimate, I think, of R squared, of the variability in the outcome that's explained by the predictors. So this would actually say 95.1% of the variability in happiness can be explained by time spent with friends and satisfaction with social life. We don't worry about RMSE. That's sort of a measure of model fit. And for right now, we're not going to worry about that. All right, what about this bottom section that's titled ANOVA? ANOVA is a very different kind of analysis, and we're going to do that later on in the semester. But what happens, similarly to how we translated or transformed a correlation coefficient R into a t-score, well, ANOVA does something like that with regressions, and it translates regression output into an F score or an F statistic, which you can see over there, F 49.64 towards the right-hand side. All of this is just talking about whether the overall model of those two specific predictors predicting the outcome, whether that's a significant model, whether those two predictors combined actually do tell you something about the outcome. And so all of this gobbledygook, the sums of squares, the degrees of freedom, the mean squared, the F and the P, all of that combined is just telling you, really, do these two predictors, do they do a good job of predicting and having some kind of effect on the outcome. And the only thing we're really interested in right here with all of that bottom section is the p-value. If the p-value is less than 0.05, then this is a significant model overall, and we should continue looking at more specifics about the model. If the p-value is above 0.05, then it's not a good model. It's not a significant model, and the variables that you have included as predictors don't really have any effect on the outcome, and they're not good predictors. So you would not continue looking at it. But right now we have a p-value of 0.005, which is definitely less than 0.05. So we can conclude at least the overall model of the two predictors predicting the outcome is significant. And now we would be curious to look more specifically at how significant and what are the effects of each predictor variable alone on the outcome. Okay, so this slide demonstrates the different unstandardized and standardized regression weights or regression coefficients, as we call them. And so the unstandardized regression coefficient is B, that's the slope. The standardized regression coefficient is beta, okay? So what this is showing is on the first row we've got the intercept, right? And that's the value of the outcome when all of the predictor variables equal 0. We don't look at the intercept all that often in multiple regression. It's much more useful in linear, simple linear regression because that helps you establish what the trend line equation is, and then you can manually input values of the x variable and then calculate the predicted value of the y variable. Here, we don't worry too much about the intercept for multiple regression, but we do care a lot about the next two rows. So the row for time spent with friends. Let's walk through what these numbers are saying. The unstandardized regression coefficient of 0.956, that is the slope, that's B. And so what that's saying is for every 1 hour increase in time spent with friends, we would expect happiness to increase by 0.956. And that's 0.956 in the original units of whatever scale we measured. So it's just, if it's a scale of 1 to 10, then this is just 0.956 happiness units, essentially, on that 1 to 10 scale. The standardized beta coefficient of 1.462, that is saying that for each 1 standard deviation increase in time spent with friends, we expect 1.462 standard deviation increase in happiness. All right. The t statistic is basically like we just, when we take correlations and we can convert them into t statistics, you can do that for basically, now this is a simple linear regression of just the effect of one variable, time spent with friends, on the other variable, happiness. And the t statistic, 6.267, is significant at a p-value of 0.008. Nice. Okay, so that means that in this multiple regression, again, these are the slopes and the unstandardized and standardized coefficients, regression coefficients, independent of satisfaction with social life. So controlling for satisfaction with social life, time spent with friends is still a significant predictor of happiness. How do I know that? Because the p-value is less than 0.05. So it's a significant predictor, and the unstandardized and standardized beta weights, or unstandardized slope, I guess, and the standardized beta weight tell you exactly how does it affect, or how is it related to the predicted value of the outcome. Now, satisfaction with social life has a slope of negative 0.278. That's interesting. The standardized beta coefficient is negative 0.559. And you can see that the t-score is negative 2.394 and the p-value is 0.096. 0.096. Well, 0.096 is larger than 0.05. So this is not a significant predictor of happiness when controlling for time spent with friends. So satisfaction with social life is not a significant predictor of happiness when controlling for time spent with friends. And you can think about why that might be, right? Well, time spent with friends and satisfaction with social life, there's going to be overlap between those two variables. And so it turns out that time spent with friends is actually a much better predictor of happiness, whereas satisfaction with social life, originally its effects on happiness were more so to do with the fact that it overlapped with time spent with friends. And so satisfaction with social life, when you take out the effect from that of time spent with friends, it's no longer a significant predictor of happiness. Another thing worth noting is that even though time spent with friends is a significant predictor of happiness, meaning it has a significant effect on happiness, we still can't say that time spent with friends causes happiness. Because again, these are just things that we've measured on different participants kind of all at the same time. We didn't use any randomization to different groups. This wasn't experimental. So how your data is collected tells you whether we were talking about correlational results versus experimental and causal results. So from the data that we have, we can't say that time spent with friends causes happiness, but we can say that time spent with friends predicts happiness. So in regression, we use the word predict. In correlation, we use words like associated with, or related to, or linked to. In regression, we say it predicts the outcome. All right, let's take a new example. I want to see if school performance, measured as GPA, and sleep, measured in hours of sleep, predicts happiness, and happiness will be on a scale of 1 to 10. So I want to see if these two variables predict happiness. And let's say this is the output that I get. I want you to tell me which of the variables, or maybe one variable or both variables, are significant predictors of happiness. Well, you can see, according to the p-value, that GPA has a p-value of 0.152. That is more than 0.05, our cutoff value. So that is not a significant predictor of happiness. GPA is not a significant predictor of happiness when controlling for sleep. But sleep, the p-value associated with sleep is 0.007. That is less than 0.05. And so we would say that sleep, when controlling for GPA, or independently of GPA, is a significant predictor of happiness. All right, now let's pay attention to the standardized beta weight or beta coefficient and the unstandardized regression coefficient. So for GPA, I want you to tell me, although this is not a significant predictor, I want you to tell me the interpretation of the unstandardized correlation, or rather unstandardized regression coefficient of 0.30, which is the slope. I want you to tell me exactly what does 0.30 mean? How do you interpret 0.30? Okay, so this is how you would interpret 0.30 in this case as the slope. This means for every 1 unit increase in GPA, we would expect happiness to increase by 0.30 on the scale of 1 to 10. All right, so GPA, for every 1 unit increase in GPA, we would expect happiness to increase by 0.30. For sleep of 0.79, the slope is 0.79. For every 1 hour increase in sleep, we would expect happiness to increase by 0.79, right? So the units are unstandardized because they're whatever the original units are for sleep, which is in hours, and whatever the original units are for happiness, which is just a scale of 1 to 10. Whereas the standardized beta weight or standardized beta coefficient is in units of standard deviations. And so sleep, as a 1 standard deviation increase in sleep, corresponds to a 1.63 standard deviation increase in happiness, whereas a 1 standard deviation increase in GPA is associated with a 0.45 standard deviation increase in happiness. And by the way, the standardized beta weights are nice because they tell you the relative strength of the effect of the predictor on the outcome. And so not even looking at the p-values, if we just looked at the standardized beta weights, we could see that sleep is a bigger number. 1.63 is larger than 0.45, which means sleep is a stronger predictor. Let's say it like that, a stronger predictor of happiness than GPA. And it should be noted that if you have negative standardized beta weights, you just take the absolute value. So if we had another predictor variable that was something like health, and it had for whatever reason, it had a negative standardized beta weight, although that wouldn't happen. I guess it would be illness. It had a negative standardized beta weight of negative 2.2. Well, that is actually larger than the effect of sleep, which is 1.63. So you'd have to take the absolute value of negative 2.2 and say, wow, it looks like illness is actually a much larger contributor or predictor of happiness than sleep or GPA. Anyways, hopefully that was interesting and useful. Thanks for your attention. Okay, nice work. We'll see you in the next chapter.